Good morning, everybody. Welcome to the next phase of your life in Physics 2B. Congratulations for being willing to come back after yesterday, right? So we'll move forward. Again, this is like another hard unit like the one we just had. What was hard about the last unit? Everything? That's a fair answer, okay? I mean, there was vectors in it, right? There was 2 dimensions, sometimes 3. There was a lot of visualization. All of that carries through, okay? What?
Oh,
the vocabulary. That's always a problem, right? Okay. And I mean, just as a slight tangent, why do scientists use big words?
Sound smart?
To sound smart? That's mostly what it is, actually. Psychologists study this phenomenon, right? Big words, other than making you sound smart, actually convey precise information in shorter terms, right? So Dr. rattling off all of those terms can actually convey quite a bit of information very quickly. To bring it into words that are more like everyday just takes longer to say and things like that. So there's reasons behind it, but we've discovered that it's mostly a flex on anything. But I lack any other terms to really describe what's going to go on. And what I want you to do is I want you to turn to each other and make a list of everything you know about magnetism in the next 2 minutes. Go. Anything you know about magnets or magnetism, go.
Well, not scary, but I've like magnets are really cool.
I know more where the cells.
That would be one of the worst things ever being an MRI machine and having like, I don't know, staples or something.
I don't understand it.
Staples, if you're surgical staples. I'm sure we just did the physics on why you choose.
Yeah.
I know even if something's not magnetic, if the magnetic like field is strong enough, it'll still affect it.
Yeah, because it messes up the
All right, what'd you come up with? Let's make a list. Shout them out.
The magnetic fields are strong enough, non-magnetic materials still are affected.
Okay, so there's strength. So you use the F word. Okay, fields. Right? Okay, so is there a magnetic field? Yes. What do you think it might be? It's good morning, isn't it? You know about electric fields now.
Is it an electromagnet?
So what's a magnetic field? If an electric field is a pattern of electric forces, then what's a magnetic field? Pattern of magnetic forces, right? Okay, all right. So we know it consists of a field. Do we know anything about the field? Okay, what else do you know about magnets?
Like charges, opposites attract.
Oh, okay, but it's not plus and minus, right? What terms do we use to describe the parts of the field? It's not positive and negative. That's electric field. What was it? North and south. Okay, so there's north and south poles to a magnet. Okay, we'll talk a little bit more about that in a bit. Okay, so it's not plus and minus, it's north and south. Okay, what else did you figure out or remember about magnets? Magnets lose charge. Okay, so magnets don't, technically everything has charge, right? But this is a unique thing. So remember how we talked about fundamentally everything in the universe has charge? Like if it has mass, it has charge too. Well, it also has tiny magnet. Okay, like it has magnetic field. all the way down to the electrons, right? So again, this is a fundamental aspect of the universe, of our creation, that things have mass, things have charge, and things have magnetic field. It's just that a lot of things don't stick to each other, right? So even though the atoms in my keys and the atoms in the glass and everything like that have tiny built-in magnetic fields, those magnetic fields do what? They cancel, right? They sort of, in a kind of magnetic way, they neutralize themselves out, okay? A bar magnet, a permanent magnet, like the kind that you put on your refrigerator or something like that, right? Okay. They have an arrangement of their atoms that kind of makes all their tiny magnets add up to make a much bigger magnetic field. And as long as your refrigerator has some metal in it, some iron metal in it, it will attract. So we're actually going to get to permanent magnets at the end of this unit. We kind of start with permanent magnets as an idea, but we're very quickly going to move away from that to really get into magnetic fields. And it won't be till the end of this unit that I'll be allowed to talk about permanent magnets. And I really won't be able to talk about them until we get to quantum mechanics, because there's kind of some screwy stuff going on here. All right, anything else we remember or know about magnetic fields? Yeah.
I think the video said that the field, the pull and the force is stronger at the pole.
Yeah, okay, the closer you get to a magnet, okay, and we'll kind of flesh all this out with the equations, right? But there is something about distance, right, and strength and like location. The further you get from a magnet, the weaker it is, okay? The weaker its magnetic field is, that kind of stuff, okay? Is it a vector? Yes, it's a field. Okay, so we got to deal with that. Okay, what else? Okay, so I said it's fundamental. Again, meaning that everything in the universe has it, except the one thing that doesn't have mass, which also doesn't have charge. What's the one thing that doesn't have mass and doesn't have charge and doesn't have magnetic field? Photon. Light. Okay, photons of light. Okay, they're kind of the exception to everything. I'm going to drop a couple more here, okay, just because right now it kind of looks like the only thing that's different is instead of saying plus and minus, we're just going to say north and south, right? Okay, but that's only the beginning of the differences. We wouldn't have an entire unit of physics dedicated to this if it were just sort of an electric field with a costume on, right? This is a different thing altogether, and this is where the differences kind of start, okay? First of all, magnetic fields are always dipoles. Okay, using big words again to sound smart, Mr. Balogh. What's a dipole? An electric dipole would be a positive and negative charge together, just kind of near each other. They form something called a dipole. Magnets always come as north and south poles. There's no such thing. In science and physics, we call it a magnetic monopole. You will never find a north pole floating around by itself. A north pole will always exist with a south pole nearby. Okay? So if we're talking about the magnetic field of a bar magnet, one end's going to be north, one end's going to be south. All the way down to the electron, okay? There's one side of the electron's a north pole, the other side is a south pole. Okay? It always comes as a dipole. It's always a pair, and those pairs are never separated. If you keep cutting magnets in half all the way down to their atomic structures, they will maintain north and south poles the entire way. That's very different from electrical charge. Electrical charges, you can just have a bunch of positive over there. Okay? It doesn't need negative in order to have meaning. Okay? But for magnets, got to have both. All right, so they're always dipoles, okay? And the field gives rise to forces. If you promise to not run screening from the room, I'll tell you the next part. You promise to not run screening from the room? Tentatively, yes. So in electric fields, we were talking about the force due to Coulomb's law. In magnetic fields, there are forces, but more importantly, those forces cause torque. Yeah, right? Get out! Get out while I still can. I know torque was a bad day in physics 2A, right? Torques are hard, okay? So know that we will mention that on a couple of occasions, and we'll give you an equation to deal with it, but it's not as bad as it was in 2A. We're sort of going to skip a stone right across the surface of torques and then move on our merry way. In fact, you're about to see me pull a magic trick where we're just going to talk about forces anyway, okay? But really, technically, think about what happens with a compass, okay? A compass is a magnet, okay? It's just a magnet that has no friction to it. And if you hold that compass, right, what will it do? Point north, okay? And so what's happened is that needle has rotated, hasn't it? It's experienced a force due to the Earth's magnetic field that causes it to rotate, and any force that causes rotation is a torque, right? We're going to try and only keep it to force, but there's a couple of times we're going to have to talk about torque. Since I brought up the Earth's magnetic field, we have to segue slightly, okay? Because we need to clear up something, okay? First of all, let's do a little quiz. Which way is north? Everybody point. So half of us went, and the other half went. Okay? My wife is one of the people that doesn't know what direction it is, ever. Okay? She could not find her way out of a paper bag. Okay? Right? I go into a building, and I go down 16,000 hallways, and I know exactly where I am and how to get out.
Are you guys birds?
I don't know. I have no idea. I don't think about it, right? Okay? I'm not memorizing turns or anything, right? It's just I was born knowing that way was north. And you could put me in a room and blindfold me and I'd still know which direction it was. I must have like bird DNA or something. Right, yeah, GPS came built in with me, right? But in our family, nobody listens to mom when it comes to directions. Oh, yeah. It's just the rule. It's just, yeah. If mom told you where to go, just ask dad. So we know that way's north, right? Okay. Everybody point in the direction where Santa Claus lives. Right? Mythologically, Santa Claus lives at the North Pole, right? Okay. Everybody point in the direction of where you find penguins. South Pole, right? Are we good? Okay. This way is east. That way is west. Okay, good. We oriented ourselves, right? Okay. I wasn't able to bring the demonstration, and it actually doesn't work very well in this room anyway because our little overhead projector's stupid. Okay. But let's just pretend that I put a big old compass right here. I have a little tiny one. Let's say I have a big one, right? And I let it go. Okay. The compass will point north, as we said before, right? Okay. It's a magnet. It has a north and south pole, okay? And the Earth's magnetic field has north and south poles. But somebody mentioned a rule, I think, okay? A north pole gets attracted to a what? South pole, right? If you try to put two north poles together, you feel the push of the magnets apart from each other, right? So north poles repel each other, south poles repel each other, but opposite north and south poles will attract each other. So if on a compass, and this is true, the north pole of the magnet that is the compass points that way towards Santa Claus, then what magnetic pole is where Santa Claus lives? It's the south magnetic pole. So you've been lied to all your lives, okay? Santa Claus lives at the north geographic pole. Why do we call this direction north?
Because magnets point north.
Because the north end of a compass points that way. But in order for the north end of the compass to point that way, it must be a south magnetic pole. Okay? The penguins. What magnetic pole is where the penguins live? A north magnetic pole. It's the south geographic pole, but magnetically it's opposite. So they're saying it's the north magnetic pole and the geographic. I love this picture because it's wrong. This came straight out of a textbook, okay, right? And it's still wrong, okay, right, okay? Because the north geographic pole is a south magnetic pole because the north end of compasses point towards it. And the only way that the north end of a compass can point towards anything is if there's a south pole over there somewhere. To further complicate things, the magnetic poles and the geographic poles are not the same. The geographic pole is based on the axis of the Earth's rotation. If you draw a line through the axis of the Earth's rotation, that's where you'll find the geographic poles. The magnetic poles are offset. In fact, the Earth's south magnetic pole is somewhere in Canada, in the Saskatchewan territories. The Earth's north magnetic pole is kind of near Antarctica. It's actually not on Antarctica. It's a little bit offset in the South Atlantic Ocean. Okay, so, and they're moving. Okay, and every million years or so in the Earth's history, they've actually swapped. Okay, we're actually due for one of those reversals, and we think we might be on the way to a reversal. Reversals, swapping north to south and south to north, take about 1,000 years to accomplish. During that 1,000 years, we can actually end up with octopole fields. Those are fields with 8 poles, like 4 dipoles all arranged on each other. So sometime in the next 1,000 years, compasses are not going to be doing what we need them to do. Okay? Don't worry, your planes are not going to crash and your cars are still going to know where to go because we don't actually use magnetic navigation anymore. Magnetic navigation is a backup to GPS and other systems that aren't GPS. There's inertial navigation systems where the planes and the cars and everything just figure out accelerations and they figure out where they are. Okay, so okay. Have I been destroying childhood dreams so far? Right, with where the north and south poles are. To be clear, where does Santa Claus live?
South magnetic.
He lives at the North Pole, but that is the south magnetic pole, right? Okay. All right. Okay. I'm going to, before we get to a quiz, let's kind of lay out some of this stuff. And what I'm going to do is I'm going to have you drink from the fire hose for just a little bit, okay? Because I just kind of want to get these things down, and then we'll deal with their consequences, okay? So, first of all, okay, let's go back, because we've done this before with electric fields. Remember how we started with Coulomb's law and we said this is the force between charges, right? And then we used those forces to develop a pattern that we called the electric field. We're going to do the same thing, okay? We're going to start with the force that magnetic fields exert on things, and then we're going to build that into the magnetic field. So let's start with the force first. And without any kind of proof, I'm just going to tell you what it is. And this is the magnitude of it, okay? Q is, what's Q? Charge. So first and foremost, the magnetic field, as we're going to deal with it at first, will be, the force due to the magnetic field will be experienced by charges. So we're going real simple here, right? No permanent magnets, none of that kind of stuff, just a single charge. So a single charge can experience a force as long as it's moving. So there needs to, this charge must have velocity. So magnetic fields are doubly difficult because they are dynamic structures. In other words, with electric fields and forces, everything could be static, right? We could just put the charges somewhere and they'd feel forces and there'd be an electric field. With magnetic fields, our charges have to be moving because what's the force on a charge due to a magnetic field if there's no velocity? It's 0, right? You put in V0 and it's gone, okay? And The strength of the magnetic field. I apologize, but when physicists were inventing this, they had run out of the letter M. Okay? That's just B. B is the symbol for magnetic field strength. Just like E is the symbol for electric field strength, B is the symbol for magnetic field strength. And then because everybody loves a little dose of trig with anything, there's a sine theta on there. Okay. We have to kind of break this down, okay? So let's rearrange just slightly. What's a magnetic field in this sort of context, right? Well, it's a force divided by stuff, right? All I did there is manipulate sort of mathematically, right? But we can find the magnetic field if we know the force on a moving particle. What's the theta? So let's just pretend that there's a magnetic field like pointed this way, okay? And then I put a charge in that field, okay? And let's say that the charge is moving to the right. So the field's to the right and the charge is moving to the right. The force on this charge will be 0. It has speed, doesn't it? That's not 0. What's the angle between the velocity vector and the magnetic field vector here? And what's the sign of 0? Okay. So in order for this force to be as big as possible, which way do the charges need to go? Not 45. They have to move perpendicular, right? So that the angle would be 90 degrees. That's how you get maximum force, right? And then you get everything in between, right? Kind of depends on if there's another angle. So the angle in this equation is the angle between the velocity vector and the magnetic field vector. Sorry, it's just, we just make observations and we write down the math that fits the observations, and this is it. So not only does it have to be moving, the velocity has to have some component that's perpendicular to the field. Can this get any worse? Yes. Velocity, is it a vector, scalar, or elephant? It's a vector. Magnetic field, is it a vector, scalar, or an elephant? It's a vector. Force, is it a vector, a scalar, or an elephant? Okay, so we're going to multiply two vectors together and get another vector. That's exactly what we're going to do. Back in physics 2a, we multiplied two vectors together to get a scalar. I don't know if you guys remember the dot product at all. We may have skipped it a little bit. It's kind of an optional thing. I think I skipped it last semester. I just sort of glossed over the fact that you can multiply two vector things together, like force and displacement, to get work and energy, right? Okay. There's different ways to multiply vectors. One of them is called a cross product, if any of you have been in enough math to get to vector math, right? So we're talking cross products here. Don't panic if you don't understand that. You're like, Mr. Balogh, trigonometry was the prerequisite here, right? Yeah, we're going to keep it that simple, okay? But like, realize that we are multiplying vectors here to get more vectors. And this comes back to bite us when it comes to the directions of the force. But before I get to the directions of the force, we do need to come back to our list here, and we need to make sure that you are clear, okay, on one very important difference between magnetic and electric fields, okay? Magnetic fields, okay, form closed loops. Always. Okay. The rules for electric fields. Do you remember where they started, where they ended? Start on positive, end on negative. Okay. Magnetic fields don't start and stop. Magnetic fields are loops. This gets really confusing because a lot of textbooks will draw a bar magnet and they'll say, okay, this is north, this is south. And then they'll draw the field lines coming out of that bar magnet, and they'll draw it like this, right? They'll say whoops, come back, there we go. Stop it, there we go. It keeps trying to drag my thing. They'll draw like pictures like this, okay? Do you see that there's a direction to that field? We say that the field emerges or comes out of north poles. The field points away from north poles. So all fields have a direction or a flow, and this flow is away from a north pole. And then that field will turn around and go into a south pole, forming a loop. What they don't draw, and they usually do it for clarity, is the field line that's inside. There's a field line inside, okay, that completes the loop. But it's often not drawn that way, okay? So again, it comes out of north poles, goes into south poles, right? But also continues through the magnet, okay? So magnetic fields always form closed loops. They don't start on north and end on south, although sometimes in the pictures in the textbooks and online and all that kind of stuff, ChatGPT will say it starts at a north pole. More technically, it comes out of a north pole. Because again, there's no magnetic monopoles. There's no north pole just sitting there where magnetic field can start from. It's always a north and south together, and so they'll always be connected. It's one of the fundamental things that separates magnetic fields from electric fields. Okay. However, right, all of the other sort of like field ideas stay. You can't have lines that cross each other, right? They can't overlap or touch. They'll sort of be pushed away from each other, that kind of stuff. Do you see how here I drew them and I didn't like connect them all the way around, right? I'm running out of space here. So I can still do that funky thing where I send it to infinity as long as I come back, right? From infinity around the other side, okay? We will draw, just again, to add to more confusion. Here's the north end of a magnet, and here's the south end of a different magnet. Do you see how I'm not drawing? Like I'm not saying, well, there's a south over here and there's a north over here. I'm just sort of looking at the specific end of the magnet. What would the field look like here? Well, the rule is it comes out of north and goes into south, right? So it goes out of north and into south, and it will take the shortest possible, cleanest, easiest path to do that. Okay? I know it doesn't look like a closed loop, but it is. Because it will continue to the North Pole and come out of this North Pole, come back around and go to this South Pole. But we often don't draw all this extra stuff because really what we want to look at is what's going on down here. Okay? So just try to like lodge it in the back of your brain. This is going to come back later. That magnetic fields don't start and stop anywhere. We often draw that they do just to make the drawings clearer. But in the back of your mind, you just have to remember they form closed loops. There's no beginning and end to a magnetic field line. Doesn't start anywhere, doesn't stop anywhere. It flows. Okay. Okay. Back to this. Okay. A force is a vector. Actually, you know what? Let's do a quiz first. Let's do a quiz. Let's not confuse the waters anymore with vectors. Let's try to stay away from vectors for just a little bit more. Stay in our innocence, okay? And we'll give you the real grown-up version here in a second. Let's do a quiz.
Do you by chance have any?
Yeah, I do. How you know stuff. You just have to have somebody tell you sometimes, right? This is the way it is. Okay, so now we're going to add directions. We had the example before. So this is a case where the magnetic field doesn't look like a closed loop, right? It does form a closed loop. It's just doing it elsewhere, and I don't care about that feature of the magnetic field. I just want to think about field pointing to the right and velocity of a charge, positive charge, moving directly upwards. Okay? We know that the force on this charge is going to be Q times V times B times sine of theta, right? Well, what's theta here? Theta is 90 degrees, and so if that's true, we just get Q times V times B. You're going to see that a lot. You're going to see the force on a charge in a magnetic field is QVB. And then you'll be like, but Mr. Balogh, you said sine theta. If they tell you that the force on a charge in a magnetic field is QVB, you instantly know something. The velocity and magnetic field are perpendicular to each other. Okay? Here's the bad news. The force, the direction of the force, is perpendicular to the velocity and the magnetic field simultaneously. Yeah, I'm going to say it a lot. The direction of the force, because forces have direction, do they not?
Yeah.
The direction, the magnitude is QVB. Okay? But the direction of the force is perpendicular to the velocity and the magnetic field at the same time. Those were the baby words. The technical term is that the force is mutually perpendicular to the velocity and magnetic field.
So is that a 45?
So that'd be like x, y, and then that would be a z, essentially.
Okay, so if the magnetic field is pointing in the x direction, horizontal, and the velocity is pointing in the vertical, your only choice for being perpendicular to both horizontal and vertical at the same time is out or into the screen. With magnetic fields, we are forced into 3 dimensions against our will. I know, it's take it up with the maker, okay? So, with 2A, we often sort of like, oh, you can do projectile motion in 3 dimensions if you want, but we're not going to, right? Oh, you can do Newton's second law in 3 dimensions if you want. We're not going to, right? We could fake or at least get a lot of predictive power out of just dealing with 2 dimensions, okay? With electric fields and electric forces, we could also do the same thing. Like a lot of times I said, remember it's 3-dimensional, but then we just did everything on a 2-dimensional piece of paper, right? We can't do that anymore. Magnetic fields fundamentally alter this constraint, and we are constrained to a minimum of 3 dimensions when we're talking about charges moving in magnetic fields. The only problem now is, which way is it? Like, we know it has to be perpendicular at the same time to the velocity of the magnetic field, but there can be 2 directions to go. Mutually perpendicular is in or out of the screen, but which one is it? In or out?
Away from, if I'm looking at it, away.
But you have to, there's got to be an argument for why. No, it's just by convention. We just decide. Okay? Physicists long ago simply decided, and this was their decision. We are going to base this on something called the right-hand rule.
Oh, you should taught us.
Okay? Everybody raise your right hand. Repeat after. No, we're not going to. Okay. I just calibration here, right? I just need to make sure that you know which ones are your right hands. Okay, you can put them down. Thank you. Okay? Okay? And did I quote Winnie the Pooh last semester? I think I did, right? Okay. Those of you that missed it. One of the preeminent philosophers of our age, Winnie the Pooh, said that I have no trouble telling my right paw from my left. It's knowing which one to start with that makes all the difference. It's deep. Very deep. Okay? So whatever you need to do, pen, tattoo, post-it note, I don't care, right? But you've got to make sure that you remember which one's your right hand. Okay? For all of you left-handed people, this is your glory moment. And I'll explain that in a second. Okay? But we define it by something called the right hand rule. There are lots of variations of this rule. I'm going to stick with the one that's in your book because it's there and it's our standard reference for this class. When you talk to the tutors, they're going to pull out a different one because in their book for the Physics 4 series, they use a different version, but it's the same. It just looks different. And you'll have to just look at them with just the saddest puppy dog eyes that you can pull off and say, but Mr. Balogh taught us the other one. And then they'll go, and then they'll remember it. Okay? So this is the one that's from your book. It's not wrong, it's just different. Okay? I like to call it the handshake rule for reasons that will become clear later. Okay? You want to hold your hand in the form like you're going to shake somebody's hand, right? Okay? That handshake, like I'm reaching my hand out to do a handshake, right? It's that symbol of, look, there's nothing in my hand, I'm not going to kill you. Okay? So you want your hand in sort of that format. Okay? You are going to put, oh shoot. My dyslexia kicked in and I'm not sure I'm going to get this right with the book. So forgive me if I don't get this right, okay? You're going to put your fingers in the direction of the velocity. Make sure I get this right. Yes, okay. No, I got it totally.
That makes sense.
No. Okay, yes. Okay, I got it. I had to go back to the one I learned in college. Okay? You're going to put your fingers in the direction of the velocity. Okay? In this case, how are we going to hold it? We're going to hold it up. And notice, due to evolution, you have this wonderful structure called a wrist. Right? And that wrist can twist around. So my fingers, right, end up being in the direction of the velocity no matter what. Is that a question, or are you just practicing, Chris? Okay, all right, just making sure. It was up high, man. You were like, yeah, it's good. Okay? So you put your V in the direction of your fingers in the direction of the velocity. You then point your palm in the direction of the magnetic field.
Okay. And the thumb will point.
And the thumb points in the direction of the force. I don't think that's the way your book does it. Hold on a second. I looked this up this morning and I've already forgotten. It probably is different. What I did was correct. It just may not be what your book does. What chapter are we in? So we'll correct this in real time. Magnetic, for here we go. And okay, I did it wrong according to the book. Okay. What's that?
Why is there two different, like, why is there more than?
You don't want to answer that question. It has to do with the Cartesian coordinate system and a lot of arguing. Okay, so the way your book does it, I apologize for this, okay? Your thumb, so handshake, okay? Your thumb points in the direction of the velocity, okay? And then, so again, with your thumb in the direction of velocity, it like can go any way it goes, right? Okay? And then you point your fingers in the direction of the magnetic field. So in this case, my thumb points straight up and my fingers point straight to the right. The facing of your palm is the direction of the force. Think of like the force like emanating from your palm like that. Okay? So you go V, and then you point your fingers in B, and the force in this case will be which way?
Away.
We say into the screen, into the page. Okay. confusing students left and right this morning. It's my job. Let's just be really careful. Okay? What direction is that? That is up. Okay? What direction is this? Down. Okay? What direction is this? This is right. What direction is this? Left. Okay? With those established, out of the page and into the page are also established. Okay? This gets really confusing because a lot of times a problem will say the magnetic field puts up out of the page. Human language is so awkward. Okay? Up out of the page would be which direction? It's out of the page, towards us, coming at you. Okay, yeah, right? So just watch out for that. I will always use up for up in the plane of the page. I will use out of the page and into the page to try to describe that third dimension. Okay? All right. Oh, and by the way, this is north, this is south, this is east, this is west. And if you're using north, south, east, and west, guess which way up is. It's out of the page.
Oh, okay.
Do you see the problem?
Yeah.
Okay? So things get mixed up. I will always be consistent. And when I'm not on the exam, just ask. Right? You said up, Mr. Balogh. Do you mean out or up? I'll be like, okay, sorry. Right. No, I've gotten pretty good at not making that mistake anymore. Okay. So this now, how do we draw this? I have a two-dimensional piece of paper, screen, whatever, right? So how do I draw in 3 dimensions?
Cut the paper and you have it like kind of
They still have not made me an app where I can draw a square and then instantly rotate it into 3 dimensions. I'm very disappointed in technology. Okay? It would be very useful, but it is not a arbitrarily easy thing to code. Okay? So 3D is actually gives computers a lot of trouble. And before you start yelling at me about video games, they are cheating a lot. Okay? All right. So you could, don't do this. You could try to do something like, well, like this, and then like that.
Oh, okay.
X, Y, Z. And then we like have to reference everything. Oh my God, this don't do this. Just don't do this. Because you end up with things like, and now I want to cry.
Yeah.
Right? Because I can't draw to save my life. All right. So this is what we're going to do. Left and right, up and down are pretty easy. We can draw those right in the page, right? Okay. To express that something is pointed into, you're going to draw an X. And for something that's pointing out, you're going to draw a dot. Where the heck does this come from? Oh, by the way, this notation in books, they sometimes have a circle around it. So they'll draw a circle with an X in it or a circle with a dot in it. We don't do that when we're writing with pencil or pen. So what's going on here? This gets violent. What is a field? Or a velocity or a force or anything? What are they? They're vectors. And what are vectors? How do we graphically write down a vector? Like draw a vector?
With a little line.
It's an arrow, right? Okay. So if I took a bow and arrow and I aimed it at you and I let go, what part of the arrow would you see if it was coming at you? You would see the tip. So a dot is the tip of the arrow coming at you. If you're standing behind me and I shoot, what part of the arrow do you see? You see the feathers going away from you, right? So that's what the X is. The X are the feathers and the dot is the arrow tip. You with me? Okay. So how over here on the left-hand side, with my green field and my red velocity, how would I indicate the direction of my force? The force is into the page with that X right there. Okay, we're going to do this a lot. We're going to practice. Okay. Give me velocity. Let's keep it easy at first. We'll play games later. Let's just do magnetic field to the right, and this time we're going to do velocity going down. Okay. Right hand rule. What do we do? Where do we put our thumb?
Down.
We're going to put our thumb down, right? Okay. So again, there's an infinite number of ways to hold your thumb down, right? But we've got to make sure that we get our fingers, which again, we're in a handshake mode, right? So your thumb goes down, but fingers have to point which way? They have to point in the direction of the magnetic field, right? So, okay, wait, stop for a second. Stop. Some of you are wincing in pain, right? If you are doing the right hand rule and you're causing yourself physical trauma, you are doing it wrong, okay? Mental and emotional distress is okay, but physical pain is not, okay? So, if you're like sitting here going, stand up and get your shoulder back into its normal socket, okay? Right? You can change where it goes, right? The one thing you cannot do is use your left hand. Lefties, I got your back. Hold on a second, okay? Right? So you're going to use your right hand. You're going to take your thumb, you're going to point it down in this case, and then you've got to orient your arm and your body such that your fingers are pointing to the right. And now which way does the palm point? Out, right? Whoa.
Oh my gosh.
Got too excited. And so I'm going to draw a dot or an X? A dot, right, for the force. I'm trying to use different colors here to make sure you can see which one's which, right? In pencil, you just get confused. Okay. If I draw that, and I say it's B, what have I just said about the magnetic field? It's going into the page, right? Okay. Give me the velocity, up, down, left, right, I don't care. Up. So here's my velocity going up. Okay? So what would the right hand rule here be? Which way are we going to put our thumb?
Up.
We're going to put our thumb up. And then what do we have to do with our fingers?
Point it in.
We got to point it in, right? Our fingers have to be pointed into the screen because that's the direction the magnetic field's going. And what direction is our force? Practice this. Quiz each other. Make flashcards. Do something. Okay? Because you need practice. Okay? This isn't come like naturally for a lot of people. Okay? What?
Is there a website that has like questions like this?
Probably, I don't know. They come and they go. I used to have some really good resources and then they all died. So I blame TikTok. Okay? And it's probably wrong there too. All right. So what happens if I do, let's do, give me a direction, any direction, up, down, left, right, in, out.
Out.
Out. Give me a direction, left, right, up, down. Left? What direction is the velocity?
No. Yeah. Yeah.
What do we know?
Oh, down. Wait.
What are we given? Force and magnetic field, right? So what direction does our palm have to go? Which way, in or out? out, right? Because we're following the force, right? Our palm has to be the force, right? We also know that our fingers have to point which way? To the left. And where does that leave our thumb? So the velocity here is up. Okay, lefties. Let's talk. Okay. You have an advantage. Okay. And the advantage is this. All the righties in the room have to do what to pull this off? They have to put their pencil down. Right? They can't use their right hands and write at the same time. Guess what you get to do? Right? You can write with your left and still do the right hand rule. Okay? But you're smarter than all the righties anyway, so it makes sense. So my best friend's left-handed. I make fun of him all the time. So right-handed people, here's the temptation. You got to do the right hand rule. You've been writing madly with some math, and now it comes time to figure out what direction it is, right? What happens? Right? And it all dies. Okay? Now, you will, because the internet is wrong, you will find the left-hand rule mentioned by AIs, by other websites, by unenlightened teachers that don't know what they're talking about. Okay? I'm kind of joking here. There is legitimately a left-hand rule. I'll explain in a second. Okay? But in my class, in my career, I've noticed that if I teach both, students just end up being confused. So I standardize on the right-hand rule because it is the standard. Okay? And we have to talk about the exception. The right-hand rule is defined for positive charges. So if an electron, like in this middle one right here, okay, if an electron were moving down and the magnetic field was to the right, you would still do the right-hand rule. You would get the force as pictured pointing out of the screen, and your very last step, because it's a negative charge, is to swap your answer 180 degrees. Negative charges screw up everything. Thank you, Ben Franklin. Okay? So just watch out. If it's a negative charge, you pretend it's a positive charge, you do the right-hand rule, and then the very last thing you need to do is flip it. I am fully aware that if you were to use your left hand for a negative charge, it will work. It does work. Okay? I just noticed, in general, for a majority of my students, as soon as you now, people are having trouble with which one's left and right anyway. Okay? And then to throw in both of those rules can be a problem. I only mention it because I am not the source of all information anymore. 25 years ago, I could say there was no left-hand rule and everybody believed me because that's what the book said. Now we have the internet and AIs and all that kind of stuff, right? And this subversive group of physics teachers that think they should be able to teach the left-hand rule. I'm going to kill them. It has its place, but at this point, stick with the right-hand rule and just remember to flip direction for when you have a negative charge. Don't be alarmed, surprised, or terrified. Well, you can pick any of those. When, during the exam, I come over and I tap you on the shoulder and I look you in the eyes, directly into your soul, and say, you just used your left hand. It's something I watch for, especially on this coming up exam, right? Okay. You'll look at me like, no, I didn't. We did this. We don't need to look at that. What the heck is this? This is your friendly neighborhood cyclotron. Okay? Why are we talking about it? Because this is a direct application of what we just learned about the forces on a moving charge in a magnetic field. One of these is down the street at the hospital over here, the university. What's the one over here in Clinton and the VA? Thank you, the VA. Okay. There's another one at St. Agnes. I don't think Kaiser's Hospital have one. I'd have to double check. Okay. Why am I picking on hospitals right now? And why would hospitals have one of these in it? This is not an MRI. You guys are all hot to trot on MRIs. We got to get to nuclear physics at the end of the course before we can talk about that. Yeah, not therapy, sort of. One of the great modern medical miracles is that we no longer have to cut you open to let the demons out. Bleeding patients is a thing of the past, except in very specific circumstances. But we can take a lot of pictures of your insides without having to get your insides to be your outsides, right? And one of the ways that we can do that is by putting radioactive dyes and tracers into, it's not a CAT scan, it's still x-rays, but the tracer, the stuff that they put in either to the blood in your brain or your stomach or whatever part of the fleshy bits that don't look good on x-rays usually, right? We need them to fluoresce and be brought out by an x-ray. Those are made by making radioactive particles that x-rays can see. Many of those radioactive elements that are used as tracer dyes have half-lives that are very short, measured in minutes, because we don't want the patient to have a lot of radiation exposure, okay? So to make those things and be able to get them to the patient in enough time for it to be medically useful, you have to make them on site. You can't have a lab in New Jersey make you iodine, whatever it is, 115, right? Because by the time they ship it to you, even with the Amazon elves, okay, it'll be gone. All the half-lives will be gone. Okay, so they have to make them on site, down in usually the basement of the hospital. They do it by using a cyclotron or something like a cyclotron. Okay, a cyclotron takes a charge, okay, and speeds it up, gets it moving very fast, and then those fast charges get slammed into elements and they become radioactive. So a cyclotron works with two D-shaped pieces of metal. We call them Ds. Okay. In those D-shaped pieces of metal, there are magnetic fields, okay? Like D-shaped magnets. Between the Ds is a gap, and in that gap, there's an electric field. So if you put a charge in the middle, the electric field will cause it to accelerate, right? It'll push it, give it a force. When it gets into the magnetic field, it'll curve, and I'll explain that curve in a second. So it curves 180 degrees, and then it gets to the gap. In the gap, there's no magnetic field, but there is electric field. So it gets another push. It speeds up again. And then it goes into a magnetic field, curves around, and then gets pushed in the gap, curves, push, curve, push, right? And with every push, it gets going faster. The radius of its spiral gets bigger as it does that, and then it shoots out the end and hits a target and makes the medicine that they're trying to make, okay? The picture in the upper right is the largest cyclotron that was ever built at Berkeley National Labs, right above the hill, above the Berkeley campus. It's gone now. This was made in the 1920s, and they used it to probe the atomic nucleus really for the first time experimentally. Okay? Why am I talking about it? Because I want to talk about the mass spectrometer. Okay? This force that I mentioned before, right, the QVB, and if I leave sine theta off, what does it mean? Everything's 90 degrees. It's like the maximum this force can ever be. This is called the Lorentz force, okay, after the person that sort of kind of put this all together, okay. So there's something going on with this force. We're not going to get all the way through the mass spectrometer. So chemists, keep your pants on, okay. We will get there. It'll be fun and exciting, whatever, okay, right? But we're going to have to do it on Thursday. But let's build the pieces as we get there, okay? So let's do magnetic field this way. Again, just to get some practice, okay? And let's do our, oh, no, I can't, sorry. Can't do it that way. It was good practice, but we'll do better practice. Let's do, yeah, let's do field this way. Okay. And then we're going to do velocity. No, I don't want to do it that way. My brain is not doing good on its visualization today. I want this thing to go. I'm doing the wrong right-hand rule, that's why. B, B, B. This used to work. I didn't draw myself a picture. I did draw myself a picture. That works. I have too many right-hand rules in my head. So we're going to do magnetic field doing, so which way is the magnetic field pointing here? In, okay. And we are going to do V like that, okay. So my particle, my positively charged particle is right there. Which way is the force on this particle? It's up, isn't it? Okay. Okay. If the force on this particle is up, then in the next instant of time, it will not be moving to the right. Which way will it be moving? Well, its velocity will get a little kick that way. Okay? So, with the velocity now like that, which way is the force? We kind of run out of ways to talk about it, don't we? Okay, right? And so if it pushes the charge that way, then at some later time, the charge is going to be going like that, right? And which way is the force?
To the left.
Which way is the force, no matter where my particle is? Perpendicular to the velocity. Therefore, it's a centripetal force. Yeah, I'm sorry. 2A's coming back. You guys remember the centripetal force? What do centripetal forces do, like gravity?
They're always in.
Yeah, but what do they do to the object? They make them go in a circle. So what will a charge do in a magnetic field? It'll circulate. The path of the velocity is not a straight line through a magnetic field. If the charge experiences a force, and it will, unless the velocity and magnetic field are the same direction, then it will begin to circulate. The mass spectrometer takes advantage of this idea, and I'll show you how to do that before. But let me leave you with this thought, okay? If you would like to see what happens when charged particles circulate around magnetic fields, then go ahead and either get on the internet and look at pictures or take a field trip to Alaska or Iceland or Greenland during the winter.
Oh.
The sky will light up with the aurora borealis. Those are charged particles that have been trapped in the earth, charged particles from the sun that are trapped in the Earth's magnetic field, circulating around the magnetic field lines, and then slamming into the gases in our atmosphere at very high speeds.
And the different gases produce different colors.
The aurora borealis is the beautiful part of the Lorentz force. We'll talk more about this on Thursday. Have a good rest of the day.
Sorry for booing.
No, we should boo about us trying to take over Greenland. We have no business.